Hello, Dr. Anna and Professor Vivian. This is the third part of our video. It's about linear dynamic time history analysis as per our schedule. So let's get into it. As per our schedule, this is the third part. First part of the video, it was about linear dynamic modeling, classical model analysis, and we have seen classical model analysis 44 and 100 story, and again response spectrum analysis in the second video. This also done. So today's part will be linear dynamic time history analysis. This is for 44 story and 100 story building, and we shall see what's going to happen. And the next part will be non-linear dynamic analysis. We are going to change our model from linear modeling to non-linear modeling, and we will perform pushover analysis and non-linear time history analysis for verification, and the results we will check. So as per today's session, this will be as per today's session. We are here, linear dynamic time history analysis, and this is the model for linear time history analysis, and I will what does it mean, and the procedure I will explain it in a minute. I will explain it in a minute, and what I did, and the modeling part will come in a minute. Just to show you the whole idea, just to remind you, this is our file. This is classical model analysis file. This is linear time history analysis. This is non-linear time history analysis. This is pushover analysis, response spectrum analysis. These are all is part of our plan. So just to show you before I start, just to show you some of the results before I explain in detail. Let me open, for example, this is bending moment under 1979 Imperial Valley earthquake. These are some of the results which was observed. Because this is time history analysis, as you can see, each time step the bending moment is changing. That is the beauty of time. This is linear dynamic time history analysis. So every second, as per the ground motion we applied on it, and the matching, and the detail I will come in a minute. This is for 40 seconds. So this is how the response of a structure, this is bending moment of a structure is changing because it is varying as per the ground motion, as per the record of the time history analysis. So again I will show you this one again in the result part. This is the combined again for the combined response for different earthquakes. This is Northridge earthquake. As you can see, this is the ground motion data which was applied in this building. So as you can see, as per the ground motion, then the response of the structure for global response, the displacement, drift, shear, overturning are changing each time step, and as you can see, this is the maximum and this is the minimum, and this is varying for each time step. This is for our 44-story building. I will come in this video again after my explanation. This is also, as you can see, starting at the beginning of the earthquake, there was no shaking, but as we go along, then the response, as you can see, this is the response. Again, this is just to show you in clear format the response of a structure. We will come in a minute just to show you. This is just for, this is shear force. Again, the shear force is changing. So this is for 44. This is for the shear wall. This is for the shear wall. As you can see, the response is changing. This is the contour. So we will come in this video. This is for 44 story. I think I have 400 story also. Output result, yes, yeah, I think I have only one video because it will okay, this is bending moment, this is deformed shapes, this is for shear wall, F22, and the shear force also. This is for 100-story building. RSM, this is registration number. This is for 100-story building. As you can see at the beginning, there is some kind of motion, but when we go along, we can see the variation. As you can see, this is how the bending moment is changing. As you can see, this is just magnified response. This is also the response of the structure. This is for the, yeah, this is for the shear wall. This is how varies. Okay, we will come back. This is what the result will be, and this is 400 story, this is 44 story. So before I try to discuss, let's go to our presentation slide now. This is our presentation slide. We are here, linear dynamic time history analysis for 44 story sample RC building for our research. So what is response, what is time history analysis, and what kind of ground motion, the matching, scaling, and extracting of the data. It's a long story, but let's get into it. Let me quickly present the linear time history analysis procedure. What is a procedure, and let's talk about it. The linear time history analysis procedure. This is code-based seismic design of structure. The linear time history analysis procedure, we have modal superposition solution. This is the response history analysis procedure, and direct integration solution. We can directly numerically solve the equation, the uncoupled equation of motion, with direct integration solution, or we can use the concept of mode superpositioning. We will uncouple the coupled equation of motion, and we can solve for each mode, and we can sum to get a response of a structure. That is, we have two parts. We are going to see these two methods. The time history analysis in the building code also, UBC, IBC, what their instruction, we will see. The selection and modification of ground motion for linear or non-linear response history analysis. This is also very important because we are going to extract data, and we will see it in the minute. Not only extracting, but we have to match it to our target response spectra. So we will discuss that also. The time history analysis procedure, software demonstration also we are going to see. And I am using, I want to acknowledge that Professor Fouad Najim, this is his presentation slide, some of the presentation slide, and I really appreciate that. This is for educational purpose. As per our discussion, we have linear and non-linear analysis type. This is structural model, seismic loading, static and dynamic. So for linear static and linear dynamic, we have the equivalent lateral force procedure, ELF procedure, response spectrum analysis, RSA procedure, or mode spectra analysis. This is a pseudo dynamic analysis because it is between static and dynamic. This is in the middle. The third one, modal response history. This is what we are going to do in this presentation. So we shall see time history analysis and response history analysis. Linear response history or time history analysis procedure. This is direct integration. Just we have to solve the equation of motion, the uncoupled equation of motion, directly with numerical integration techniques, NUMARX or other Wilson theta and other techniques. We shall see. Non-linear, we have pushover analysis. This is also part of our plan. So we have non-linear modal response history also, fast non-linear analysis. Again, we have non-linear response history analysis. The difference between these 3, 4, and 6, 7 is, in this case our model is non-linear, and in this case our model is linear, but the solution method is the same because this one is numerical method, direct numerical integration, but this one is for we have to solve the coupled equation of motion and uncouple it, and we have to solve for each mode, and we have to sum up to find the solution. So seismic design course, there are several design methods suggested in seismic code as we discussed. ELF, this is equivalent static analysis, response spectrum analysis method, time history analysis method. Equivalent static analysis method is commonly used for the seismic design of ordinary and regular building and structure. This is most of the time ELF we are use it for ordinary and regular buildings. Let's continue. Dynamic analysis method, response spectrum and time analysis are required for irregular buildings and structures. Very important structures. In structures, the seismic response is not dominated by the fundamental vibration mode. More tedious, more difficult, because if the fundamental only the first mode is not dominated, then if the higher modes should be incorporated, and if it is irregular, then we have to see the time history and the response spectrum analysis. But the response spectrum analysis is pseudo, as we have seen in our second video. The more I gave more deep explanation on the response spectrum, and we can check that. So response spectrum, once we develop our response spectral displacement, then we can derive pseudo spectral velocity and the spectral acceleration curve. Then for any our project, we can directly pick the response. But time history analysis is more effective. Irregularity, geometry, irregularity, and non-uniform distribution of mass or stiffness, structural discontinuity, etc. So vertical structural regularity and plan structural regularity, we have two type of regularities. Seismic design course, as I have discussed now, equivalent static analysis procedure, response spectrum analysis, RSA procedure, time history analysis, and pushover analysis, and we have nonlinear time history analysis as well here for verification. So linear model, this one is effective in elasticity implicitly accounted using R factor. So equivalent static analysis, response spectrum analysis, as we have seen, we have to incorporate R factor for the ductility, for non-linearity, because once we have the linear response spectrum, then we have to the elastic response spectrum, then we have to reduce it to non-linear response spectrum for the design purpose using I over R, just account for ductility and to make it economical our design. This is a concept of R. Otherwise, if we design with the linear or elastic response spectrum, it will not be economical. Time history analysis, the time history analysis as well, because our model is when our model is linear time history analysis, then we have to use R. But if it is non-linear time history analysis, no need to incorporate R, because the inelasticity is already modeled in the model, so no need to use R. So non-linear time history analysis, no need. Pushover analysis procedure, non-linear static procedure, several non-linear static methods explicitly included. We will see, we shall see also in the next video. The linear time history analysis procedure, let's see, we discussed this also in our second video, but let's go quickly. The time history analysis procedure, the full dynamic equilibrium equation is solved for each time step on the acceleration time curve. So this is our equation of motion. This is our equation of motion. So we have, as I discussed, direct integration and modal superposition. We have two types. This direct integration, we can use it for linear or non-linear models, but for modal superposition we use it only linear analysis. So the dynamic equilibrium equation is solved for each time step using step-by-step direct integration, and the history of the deformation resulting from previous time step calculation is used in computing the response for the current time step. This is another deep concept. We can see the structural dynamics course. The time history analysis is in fact a piecewise solution of the entire force histogram. Modal superposition, the dynamic equilibrium equation is solved for each time step using the idea of vibration mode. This is linear This is non-linear. We can say linear dynamic procedure, linear time history analysis, linear response history analysis, all the same. Non-linear dynamic procedure, non-linear dynamic analysis, non-linear time history analysis, non-linear response history analysis. There is a lot of name we can. So ground motion, as you can see, the input variables are ground motion, ground acceleration, UG dot co, this one UG dot, damping ratio, and circular frequency, this one circular frequency. So once we input this ground motion, the damping, and natural frequency, then the unknown parameter will be displacement. So once we solve this equation, we will have displacement. Input and output for the time history analysis: input mass and stiffness distribution, the acceleration time record as I showed you, and the scaling factor, directional factor, analysis time steps, damping to construct C matrix. Outputs: displacement, stress result. Stress are each time steps. The envelope value of response will be the output of our so additional information required for time history analysis: an appropriate set of ground motion is required. I will show you in a minute how to extract ground motions and how to match it, because when we extract ground motion, we cannot directly extract any type of ground motion, but we have to consider site class, soil type, soil mechanisms, near fault effects, design PJ or PGV, etc. So the criteria how to choose ground motion, appropriate ground motion to match it with our design spectrum, target response spectrum for our site, we will see it in a minute. I will demonstrate in depth. Additional information required for time history analysis: damping. We have modal damping and relay damping. So both of them are supported in ETABS, and the derivation and the equation was discussed in dynamics course. So let's make it fast. Seismic responses from the linear time history analysis: fluctuating global response, so base shear, base moment, roof drift, everything will be found. Story shear, story moment, story displacement, inter-story drift ratios, floor acceleration, everything can be found. And fluctuating local responses: column, PMM, this interaction curves, beam, shear wall, everything can be found. So linear response history analysis procedure, linear response history analysis procedure. As I told you, direct integration solution. We have direct integration solution. This is solve the uncoupled equation of motion directly using the step-by-step numerical integration method to get the dynamic response of multiple degree of freedom system. So in this case, we directly solve the uncoupled equation of motion and we will get the solution. But the other one is modal superposition solution, modal response history analysis procedure, and response spectrum analysis. This is also in depth explained in my second video. This one is solve the uncoupled equation of motion for each significant mode represented by a single degree of freedom system, and sum of the dynamic response to get the dynamic response of multiple degree of freedom system. That means once we uncoupled the equation of motion, and for each mode and for each floor, we will solve the response and we will sum up to find the solution for multiple degree of freedom system. But in this case, directly pick the peak response of each significant mode represented by a single degree of freedom system, and approximately combine thus peak responses to get the peak response of multiple degree of freedom system. This one also explained in my second video, but just to revise, once we have a single degree of freedom system and for the constant damping ratio and xi and mass matrix and k, we will run our system for constant damping ratio for different times, and we will pick the maximum displacement for each period of time, for example 0.5, 1 second, 2 second, 2.5, 3 second. Then we will construct a spectral displacement. Then this spectral displacement will be converted into pseudo velocity displacement by the use of the times w. Okay, w times spectral displacement will be velocity, and w square omega square times d, this one will give us also the spectral acceleration, and in this way we can find approximate solution, but this one is for dynamic solution, and it is accurate. We will see in the minute also. The linear time history analysis procedure, modal superposition solution, modal response history analysis procedure. This is uncoupled equation of motion. How we drive it, everything is explained in my second video. This is the equation of motion. So the underlying idea is, if we use mode shape matrix phi as a transformation matrix to convert a structural displacement vector ut into generalized coordinate qt, the equation of motion in qt coordinate will be uncoupled. So once we find ut, then we will find in qt coordinates, and we will multiply it with phi, then we will change it back to the u coordinate, then we will find the solution. So this is transformation equation we are going to use. So we can solve the uncoupled equation separately. Each equation will be like the equation of a single degree of freedom system. So we can effectively decompose an n degree of freedom system into n single degree of freedom system. The sum of a response of this n single degree of freedom system will be equal to the response of n degree of freedom system. The uncoupling in q coordinates is due to the orthogonality property of modal shapes. This is the orthogonality property. Phi transpose times M matrix times phi, and phi transpose times K times phi are diagonal matrix. Again we have C transpose the M matrix times C also included in this orthogonality property. Let's see. Earthquake response of multiple degree of freedom system. A shear building subject to ground displacement UGT. For example, if we see ground displacement, we have ground displacements UG, and we have a structural displacement U. So the total displacement will be UG plus UT. So as you can see, U total is equal to UG plus structural displacement times ground plus ground displacement. So in this form, in the vector form, we can see that, and U total will be UG plus UT, structural displacement plus ground displacement. So I explained this in my second video. I will just quickly explain and I will pass it. This is a mathematical formulation. As you can see, U dot T is total, so we are going to replace it with this one, U total. This is U total, ground displacement plus structural displacement. So U G dot plus U dot T will be replacing this part, U total. Then as you can see, we can take the UG part in the other side of the equation. So this is total 4 equations, coupled equation of motion. This is a coupled equation of motion we have. So we cannot solve it. If you want to solve it at this stage, we have to use direct integration method. But in the response history time analysis, we have to decouple it. So to decouple it, this is a equation we discuss now. We will change it into this equation is called modal expansion of displacement function. q coordinate, then after we brought it to q coordinate, we will multiply it to phi, then we will take the equation back to u coordinates. So transferring the above equation into the principal modal coordinate, this is the equation, and where phi is equal to phi1, phi2, phi3, phi4, q is equal to again q1, q2, q3, q4 in time domain, and phi I is equal to the i's mode vector, first mode, second mode, third mode, fourth mode. Okay, so once we have the equation of motion, now we are going to use modal orthogonality. This is a modal orthogonality property. So as you can see, this is m times u times t. So we are going to change u with phi times q dot. So we are going to change u phi times q dot plus c times phi times q dot plus k times phi times qt is equal to minus m1 ug dot. So this is the equation. We just replace the u part here. Now multiply with phi transpose. This is orthogonality property. Then we are going to multiply this equation with phi transpose. Then when we multiply this also, as I told you, see also phi transpose, this is also k. So when we multiply this part, we are going to find modal mass. As you can see, this is the orthogonality property, and the off diagonal parts are 0 and all the diagonal parts are modal masses, times q dot plus again phi transpose times c times phi q dot t. Again you can see 2 xi modal mass times omega, all this will be in the diagonal, times q dot plus again q transpose times k times phi qt is equal to this one also modal stiffness, as you can see, mu omega square. So this is also times qi, this is q, is equal to, here we are going to change phi transpose times m into minus l, just for the sake of simplification. Minus l is equal to ug dot. So l is equal to phi transpose times m times 1. This one we change it into minus l. As you can see, this means phi transpose, this is a transpose, I4, I3, I2, I1. So what does this mean? This is the i's mode. This is the i's mode, and we have 4 floors. So this is for the 4 floors. This is also m4, m3, m2, m1 times 1 vector here. This is in the matrix form. This is in the summation form. Summation of mj phi ij. So j from 1 to 4 floor, and I is the mode. Again, uncoupled equation of motion for the i's mode. Once we reach here, so the uncoupled equation of motion means this is modal mass 1. So if you multiply this equation, if you take the first row, for example, modal mu I times q dot plus 2 xi modal mass omega 1 times q dot t plus mu omega square times qt is equal to minus l ug dot t. This is the uncoupled equation of motion only for the first mode. There is no contribution from second mode, third mode, or fourth mode. So for the first mode, and for each floor, we are going to use this equation only. For the second mode, we are going to use this. For the third mode, we are going to use. For the fourth mode, we are going to use. So if we take the first line, this is the i's mode of equation. This is the uncoupled equation of motion. This is what we need, the uncoupled equation of motion. Then mu, as we discussed, is equal to this is the diagonal matrix, is a mass matrix. This one, this is modal mass. So phi transpose m times phi is equal to this one. This is in the summation form, and this is in the matrix form. Now modal participation factor, as you can see, we have mu here, Okay, so if we divide everything with mu, okay, if we divide everything with mu here, we will left with qi dot t plus 2 xi mu. Mu will be cancelled, omega times q dot. This q dot means displacement, but in the q coordinate, not in the u coordinate. We have to multiply it with phi to change it into u coordinates, plus omega I square qt, this one. Then as you can see here, Li over mu I, let's call it gamma I. This gamma I is modal participation factor. This is modal participation factor times ug dot dot. This is the uncoupled equation of motion. So if we follow this step and find the uncoupled equation of motion and solve for each floor of our building and sum the solution of each equation and find solve for each single degree of freedom system and come up with a solution for multiple degree of freedom system, this is what we are doing is response time history analysis. This is the procedure. If we don't want to uncouple the equation and we directly solve for the equation of motion, this is a coupled equation of motion, directly we solve it with numerical integrations or any type of Newmark's methods or Wilson theta or other kind of equation, this Rangi-Kutta and other type of solution. That means numerical solution, and we call it numerical this integration. Okay, we directly solving with, no need to decouple it. So that is a issue. Response spectrum analysis is no need to solve for each equation. We simply pick responses for spectral displacement, spectral velocity and spectral acceleration, and we solve as per, we construct our response spectrum and we will solve it. That is response spectrum. No need to do each solution as per response history time analysis. So uncoupled equation of motion, modal response history analysis, as I showed you now, solve the uncoupled equation of motion for each significant mode represented by the single degree of freedom system and sum the dynamic responses to get the dynamic response of the multiple degree of freedom system. This is, as I showed you, once you find the uncoupled equation of motion, okay, this is the uncoupled equation of motion, then we can solve for each. We will assume each floor as single degree of freedom system and we will sum up to find the multiple degree of freedom system. But in the response spectrum analysis procedure, we don't follow we don't solve for each question. So directly pick the peak responses for each significant mode. Only significant, we will choose the significant modes represented by single degree of freedom system and approximately combine those peak responses to get the peak response of multiple degree of freedom system. So this is the difference between response spectrum analysis and modal response history analysis procedure. So this is, as you can see, is approximate, almost approximate, because we can consider only first 3 mode or something. As per the code, only we need 80% or 90% of the modal mass participation is required. No need to add up 50 or 100 or thousands of modes of response of the structure. It's not practical. Even in the time history, response history analysis, it's not practical, because for simple frames it's okay, but when our structure is becoming complex, we cannot use this in hand, but softwares will handle for us, so we will see it in a minute also. A response spectrum analysis, as we discussed, the maximum deformation, once we have the eyes mode equation here, no need to only choose the maximums, and as you can see, ug dot we have here. Then we have single degree of freedom system, and we will run our system for different time period, and we will pick the maximum deformation and we will construct a spectral displacement. once we have our spectral displacement for a constant value of damping ratio, then automatically this is Q max. That means Ri times this is modal participation factor times spectral displacement I for the I's mode. So when we multiply it with phi, we will change it from Q coordinate to U coordinate. This is the transformation, very important transformation point where we use. So inter-story drift also the same thing, only this the upper and the lower story modal shape will be this deduct from upper to lower, then times spectral displacement I times modal mass, then modal participation factor, then it will give us inter-story drift. This is also in depth explained in my second video, you can check that. The elastic response spectrum analysis, this is also how to find force. Force is K times U, equivalent static force. So the equivalent static force for the I's mode will be K times UI max. Again from eigenvalue equation of the model, K times phi I is equal to omega square m times phi I. So we will change K, okay, K with omega square times m, omega square times m times SDI. This is spectral displacement. Spectral displacement is equal to spectral acceleration over W square. So if you change here spectral displacement, W square will be cancelled, and modal participation factor times mass matrix times phi I times SAI. This is the equation for force. This is also deeply explained, and I did Excel calculation from Professor Fornegin. I showed how it works. Modal combination, we have SRSS, absolute sum, and complete quadratic. This one also explained. Modal response history analysis procedure solves the I's modes equation in time domain, either using Duhamel's integral or using step-by-step direct integration for each significant vibration mode. This is how UT can be formulated, and QT transfer into U coordinates by multiplying it with phi. This is also, we have discussed it now. Response spectrum analysis versus modal response history analysis. UI max, this is the formula, the same as peak displacement from response history analysis, because the spectra is already based on response history analysis. But U max for modal combination, this is very important, is not equal to peak displacement extracted from response history analysis, because we have to use SRSS, not directly pick the maximum and add up. We cannot do that. We have to, once we get the response for shear, moment, or whatever global responses from mode 1, mode 2, mode 3, mode 4, we have to SRSS them from mode 1 contribution, mode 2 contribution, mode 3 contribution. We cannot directly add up. That is what it says. Okay, this is modal response history analysis in etaps. I will show you in a minute what this means. This is the form, the load case, how we are going to use it. We shall see. In damping also, how we have a rail damping or a modal damping. The linear time history analysis procedure. This is direct integration solution. We discussed already, but just for the sake of from structural dynamics course, each step discussed how to come up different solutions, like linear system, central difference method, Newmark's method, constant average acceleration method, linear acceleration method, Wilson theta method, again non-linear system, central difference method, constant average acceleration method. These all are discussed in structural dynamics courses. Just for the sake of demonstration, I brought it, and each step how to solve the equation is explained there. Linear response history analysis, direct integration in etaps also. This also, all these procedures are incorporated in ETABS also. Newmark's, Wilson theta, everything is I will show you in a minute also. Linear response history direct integration in ETABS. This is how to formulate the load case in the real demonstration. I will show you in a minute how everything what I showed you here is in the defined load cases. This one in the load cases, when we modal case or whatever, this one modify. This is the form how to generate time history analysis, linear modal analysis. As you can see here, we have linear model, non-linear model. If fast non-linear analysis, as I showed you, linear direct integration. This is a linear direct integration I showed you now. Non-linear model also, we have non-linear direct integration, and this is how we put forces in the U1 and U2 direction, and how to match and everything. I will come up in a minute, but just for the sake of demonstration now. So this is what, this is also damping, also the same thing I will show you. Time history analysis procedure in the building code. This is very important. Let's discuss here. For example, time history analysis in UBC 97. Time history analysis. Time history analysis shall be performed with pair of appropriate horizontal ground motion time history component that shall be selected and scaled from not less than 3 recorded events. So here, just what I showed you here, define load cases. For example, here modify. As you can see, we have to put pair in the X and in the Y direction, and the appropriate time history shall have magnitude, fault distance, and source mechanisms that are consistent with those that control the design base earthquake or maximum capable earthquake, MCE level or DBE level in your site. We cannot directly extract any type of data. We have to find real compatible ground motion with our site. We will see it also when we extract it. I will show you in a minute. So here also they recommend we can use 3 record events, but 7 and 11. For our case we use 11 cases, and for 3 also is allowed. Where 3 appropriate record ground motion time history pair are not available, appropriate simulated ground motion time history pair may be used to make up the total number required. So we can artificially also generate. For each pair of horizontal ground motion component, the square root of the sum of the squares SRSS of the 5% damped site spectrum, specific spectrum of the scaled horizontal component shall be constructed. The motions shall be scaled such that the average value of the SRSS spectra does not fall between 1.4 times the 5% damping spectrum of the design base earthquake for the period from 0.2 t second to 1.53 second. I will show you this one, what does it mean, because once we have our response spectrum, the design response spectrum, and when we match it, the matching parameter from 1.4 times, this is from 0.2 second to 1.5 second, 0.2 second to 1.5 t second. In this, if our design response spectrum is like this, so the matching parameter is not allowed to be below the design response spectrum. 1.4 times the response spectrum is not allowed. It should be upper. If it is down, then we have to scale it up, or we have to find another data. Each pair of the time history shall be applied simultaneously to the model, as I showed you earlier. U1, UX simultaneously applied in the building. This is UBC 97. The parameter of interest shall be calculated for each time history analysis If 3 time history analysis are performed, then the maximum response of the parameter of the interest shall be used for the design, if we use 3. If 7 or more time history analysis are performed, then the average value of the response parameter of interest may be used for the design. So we can use the mean, but if you use 3, we can directly pick the maximum value. Otherwise we can use the mean. So I will show you in the system match how to find the mean value, but the takeaway here is, once we have the design response spectrum, our design response spectrum, whatever ground motion we extracted from peer website or USGS, whatever, when we forcefully match it with our design response spectrum, so we are forcing it, the response will be forced to be the same. So whether we are using the mean value or the matched value of the ground motion acceleration, the result is most probably the same, because we are forcefully forcing the ground motion we extracted from peer website into our design response spectrum, and from 0.2, as we have seen, 0.2 second until 1.5 second, the parameter should not be less than 1.4 the design response spectrum. So we are forcefully matching it. So the global response or the local response of the structure most probably will be the same. Elastic time history analysis. Elastic time history, this is all the sections you are invited to read. Extraction of results after the application of ground motion. So we cannot simply use, I will show you how to extract and design. Again, the time history analysis in UBC 97, nonlinear time history, that one is linear time history. Nonlinear time history analysis shall meet the requirement of section this, and the time history shall be developed and result determined in accordance with the requirement of section this. Capacities and characteristics of nonlinear elements shall be modeled consistent with test data or substitute analysis. Considering the importance factor, the maximum inelastic response displacement shall not be reduced, because this is the model is already nonlinear. No need to reduce it with R factor, I over R or CD factor or whatever factor we will not use, or overstrain factor we will not use it here. Design review. Most of the time this nonlinear time history analysis is for design review. When nonlinear time history analysis used to justify structural design, a design review of the lateral force resisting system shall be performed by an independent engineering team. So this is for verification purpose. Once we make pushover analysis, linear history analysis, response spectrum analysis, or modal analysis, this analysis will help us for verification purpose. So what we are doing, what we did in our project also, after we design everything, then we verify it with pushover analysis, and the pushover analysis result also verified with nonlinear time history analysis. So this is for review purpose. Now let's go to IBC 2000. The same is true with UBC 97. I didn't see any change, only the change is but in this case dynamic analysis procedure in IBC 2000, the same thing here. Modal response spectrum analysis, linear time history analysis, nonlinear time history analysis is the same procedure. And time history, the same thing. Time history analysis shall be performed with a pair of appropriate horizontal ground motion time history components that shall be selected and scaled from not less than 3 recurred events. The same thing UBC 97. Appropriate time history shall have magnitude, fault distance, and source mechanisms that are consistent with those that control the maximum considered earthquake MCE level. So when we choose our ground motion data, all this should be the fault mechanism, distance, source mechanism, everything should compatible with our site. So MEC or DB level, where 3 appropriate recurrent ground motion times 3 pairs are not available, appropriate simulated ground motion times 3 pairs shall be used to make up the total number required. For each pair of horizontal ground motion component, the square root of the sum of square SRSS of the 5% damp site specific spectrum of the scaled horizontal component shall be constructed. This is also the same, no change. The motion shall be scaled such that the average value of SRSS spectra is not less than 1.4 times the 5% damped spectra of 2/3 that maximum considered earthquake for a period from 0.2 t. The same UBC also 0.2 until 1.5 second. The matched response spectrum should not be less than 1.4 times. This is 2/3 means once you have MEC level, then you multiply it with 2/3, you will change it into dBE level. The parameter of interest shall be calculated for each 3-time analysis. If 3-time analysis are performed, then the maximum, the same thing again, of the parameter of interest shall be used for the design. If 7 or more times 3 analysis are performed, then the average value of the response spectrum of interest may be used for the design. Until now, we don't have any change. UBC 97 and IBC 2000 are the same. Non-linear also the same. This is for review purpose. For review purpose, as you can see, for non-linear, we don't need. The response shall not be reduced by R over IE because the model also by itself is non-linear. We will force deformation curve for non-linearity will be assigned for each column, beam, and the non-linearity of the structure will be used. This will be our next video. We will discuss about non-linear pushover and the response history analysis. So if our system, our model is linear, no need, non-linear, no need to reduce it by this factor. The selection and modification of ground motion for the linear or non-linear response history analysis. This is very important. So how we select and modify the ground motions from different websites. As you can see here, we have USGS earthquake catalog, peer ground motion, British Geographical Survey data, Cosmos ground motion data system, KNet. All of them have the data, so we can extract. But for our case, and the most popular one is peer ground motion, so we will use it. As you can see, we can. So just building seismic safety committee. This is the committee every year. NEHRP every 1 year. ASC 7. So every 2 years IBC 2000. This is the family of building codes, how it's developed. Then ASC 7 in 05 uniform hazard approach. This is the maximum considered earthquake, 2% of probability of accident in 50 years, and dBE level, as I told you, 2/3 of MC will be dBE. IBC 2009, the same as ASC 705. These are the same, but starting from ASC 710, response risk target approach of or performance based approach was introduced. So PE replaced with P collapse. So instead of PE, they call it P collapse. So MCE R risk is equal to, instead of 2% of PE in 50 years, they call it 1% of P collapse in 15 years. And the design dBE level also 2/3 of MCE risk. This is the same for IBC 2012, same as AC 710. So this is a change. This is a change. Instead of 1%, now they change it into instead of 2%, they change it into 1%. So general code procedure AC 7 and onward. This is the step. Let me go through very fast. Step 1, SS and S1. Just you go to to the map, and from your location you will read from the map SS and S1 values. On what these maps are different from MCE level. This PSHA, probability seismic hazard map, they are modified for the risk target probability of collapse, as I showed you, 1% of this one, 1% of P collapse in 15 years instead of 2% of probability of accident. So for example, we are here. So let me show you this one. I think I have 104. You don't have here? I thought I had the map of, yes, this one. This one is a map, SS and S1. So if your site is around here, you go here and read the SS and S1, the SS and the S1 value from here. Then let's go 104. Once you read from the map, once you get SS and S1 value, then soil classification, then from your soil classification based on the V30 shear wave velocity value, SPT value, or undrained shear strengths, you will find your soil type. And once you get SS, S1 and these values, again from the table, in the my second video I explained it here, you can find FA and FV values. Okay, FA and FV values. Once you get FA and FV values, calculate SMS. SMS is equal to FA times SS. SM1 is equal to FV times S1. Then calculate SDS, desired level. This is 2/3 of MS and SD1, 1 second spectral acceleration, 2/3 of SM1. So this is how we do. The factor 2/3 was originally proposed for California. The engineers decided to design on 2/3 of the MEC. Later it was widely accepted. So let's continue. This is 5th step. Now 6th step, determine TO, T long and T short. They are the function of SS and S1. Then construct the target spectrum using code equation. Once we get these points, we can directly use. Assign occupancy category or risk category. This is also from the code. Identify the seismic design category used to design A, B, C, D, E, F. This can be identified from the detail of a structural design process. So SDC, structural design category A, structural design category D. Then after that you can see here 0.4 times SDS. Once we get the SDS times 40% of SDS will be here, the peak PJ. Then when we you have SDS already, as we see. So as you can see, TO is 0.2 times SD1 over SDS. Once we get here, let me go back. Once we get SDS and SD1, then here just SD1 over SDS times 0.2, it will give you T0 here. This is constant acceleration area. This is constant velocity area. After that we have constant displacement area. This is for very long, the time period more than 8 seconds or 9 seconds. This is the area for long. For our 100 story will be here. For our 44 story will be around here, no problem. Around 4 seconds is enough. So we have TS. Then this is for T1. For 1 second we can find SD1 here. And TL is long time transition. So most of the time 8 seconds or something, but the equation is this one, SD1 over TL over T square. as per your time period of your structure. This is SA, this is SD1 over T. This is the equation. S days 0.4 plus 0.6 times T over T1. SA is equal to S days. This is the equation. So you can read this also, what is shear wave velocity and how to. But ASC 4106 size classification the same as ASC 710. Now they included other factors. So as you can see, we have B1. This is B1. This is the equation of B1. B is effective viscous damping. So when you make your damping is 0.05 for 5% damping, then B1 is equal to 1 and you can get the original. But when B is different from 0.5% damping, then the equation will be modified according to B1 factor. This is a modification. This is a modification B1. So times 3 deployment for dynamic analysis of a structure. So this is ground motion prediction equation, PSHA, DSHA. This is also a deep concept, how to generate probabilistic seismic hazard assessment and deterministic seismic hazard assessment, deaggregation, what is deaggregation, conditional mean spectrum, times 3 development, take past recorded earthquake and modify them, use Green's function to develop synthetic time histories, physics-based prediction of time history, simulation, and others. Selection of ground motion from peer ground motion website. This is a website. So this is my email address. I am professionalcivilengineer@gmail.com. So okay, I will demonstrate this online now. Before that, there is one concept I want to show you here. It's not visible. Okay, let me open and we will discuss this R rupture and RJB, this Jenner-Boer distance, closest horizontal distance from the site to the projection of the surface rupture. So RJB means, for example, if this is our fault, this is directly, I took it from Professor Ford. This is, so this one from here to here, the closest distance, this is R rupture. But if we project it to the surface and from the surface to the site, this is called RJB. This is the easiest explanation of what is R rupture and RJB. So once you know your site, R rupture is the closest distance from the rupture and the projected one is RJB. So let's go how to extract our data for so scaling. I will come. So let's go to Google. Let's go to Google. So peer website. This is peer ground motion database. As I showed you, you can use different. I already signed in. This is my email. I am professional civil engineer. If you don't have account, you can register. And we have two databases here. This is NJ West 2 shallow crystal earthquake in active tectonic region, and this one is central in eastern North America, but mostly this is where we need. This is a site. As you can see, this is no scaling, PGA, this wave spectrum, use defined spectrum, ASC code spectrum, whatever you need you can use. But for our demonstration, let me go to no scaling. Once you come to this page, So as you can see, we have RSN record characteristics. This is the registration number. If you know the RSN, the number of your the any earthquake database, you can use directly that one. Or if you know the event name also, you can use the event name. A station name, if you know the station name also, we can use the station name. Fault type, for example, strike slip or normal obliques, reverse obliques, SS plus normal, SS plus reverse, normal reverse. These all are about earthquake engineering, geology. You should know what is strike slip, fault, everything. The magnitude, if you want which magnitude you need. RJB and R rupture, as I showed you now, what is RJB and R rupture. Once you know the closest distance from the fault, that is R rupture, and RJB will be the project distance from the site to the fault. This is V30, shear wave velocity of at 30 meters per second. This is also from the code. For us, we use as per the code. This is minimum and maximum DS and D5 and D95. This means the earthquake, the energy between 5% and 95. That means around 90% of the energy of the earthquake concentrated in that area. So we use D5, and so we will make the time limit from where to where. And this is a pulse like record. Pulse like record means if the earthquake is between 10 kilometers, very near, it is pulse like. So if you have pulse like, we can make it pulse like, or if it is not, no pulse like. Then this will be maximum number of record we need. We will use from here. So for us, for example, if you know, for us, for example, this is the RSN number I used in my site. Otherwise, you can fill everything and you can generate, then search result. You can fill everything and you can generate. So this is for us. Once it is finished, it will give us. This is 7 earthquake, as you can see. Now we have 7 because I put directly the RSN number. As per the RSN number, directly it gives me. So the first one is this is SRSS record sequence. This is the record sequence, and this is scaling factor. This is, as we have seen, DS and DS 95 from the this is DS and DS 95. Then this is the intensity. This is event. The event, this is Imperial Valley 06, Mamos Lakes 09, Loma Parita, Landers earthquake, Northridge, Chichi, Taiwan, Parkfield. All these are the earthquake, and this is the year 1979, 1980, 1989, 1992, 1994, 1999, 2004. The station, this is the station where the earthquake was recorded. All are written here. Magnitude also, this is the magnitude. As you can see, the maximum is 762. And this is a mechanism: strike slip, normal obliques, reverse obliques, strike slips, reverse strike slips. RJB, R rupture, as you can see. This is VS 30 shear wave velocity, and you can find a lot. Then here, as you can see, horizontal, and this is the data. This is dot 82. This is dot 82 from peer website, but others also have another extension. So we have dot 82 files for X, Y, and Z. So once we find this, as you can see, this is the mean of all this one. Okay, all 7 we have result, we have 7 ground motion. So we have plus standard deviation and minus standard deviation. As you can see, 1 standard deviation and 1 up and down. So this is the mean one. If you put here, it will give you spectra arithmetic mean plus standard deviation, this one. And if you do this is minus standard deviation, and this one is the mean. So you can find the mean also. And you can see, if you want to see anything, you can view. If you want, you can view. This is for this earthquake. This is Imperial Valley 1979 earthquake. So as you can see, this is the mean, this is standard deviation 1, this is standard deviation 1, standard deviation down. This way we can see. Then you can download search result, metadata, spectra, download time series, record metadata. So if you make it download, then it will directly download, but I already downloaded it, but I can show you. If you say download, it will give you, this is not scaled, you have to scale it. You can say okay, then okay. So it will start download, it will start download. Then until it downloads, the download will start in the zip folder. But for us, I already downloaded 11 ground motions. Let me show you. For us, I already this ground motion from peer website 7 and 4, 11 ground motion data was sorry, 11 ground motion data was downloaded. As you can see, this one is RSN 164 Imperial Valley. This is 237 again Imperial Valley 164 and 1 each. For each we have 9, because in the x direction we have a spectral acceleration, spectral displacement, spectral velocity. Again 82, the same thing. In the y also we have 3, in the z also we have 3. So for each record station we have 9 datas. So for our case we need only this one. So as you can see, this we can open it in the notepad, and we can see the format also. Let me open it, for example. As you can see, this is peer NJ strong motion database record Imperial Valley 06. This was happened in 10/15/1979. Cerro Perito 147. This is the station. Then acceleration time series in unit of G. This is very important because this is in the unit of G. Then when we go here in our data, we have to check which show unit form. So our acceleration data working should be compatible with this one. For example, where is acceleration? I think this one, yeah, millimeter per second square. As you can see, this is millimeter per second square. We don't have other acceleration, force, moment. Yeah, so once we know that our acceleration is millimeter per second square, then if you know this this one is in G, then we have to multiply by 9810 just to make compatible with this one. So as you can see, we have 6,382 points, 6082 points, and every 0.01 time steps. As you can see, 0.01 time steps. So each point we have 1 2 3 4 5, and 1 2 3 4, it will start from fifth. So in this way we can see this is now we have full data, and we are going to match it, scale it for our with our design spectrum for our site as per the code. As per the code, let me show you here in our when we discuss UBC 97, here UBC 97, what was we discussed? Just as you can see, UBC 97, when we match it, the period from 0.2 second to 1.5 second, when we match it, it should not be lower than 1.4 times the 5% of damping spectrum. We have already the design spectrum, so I will show you in a minute how to match in the Sesamo match and in our ETAPS. So in this way we can extract, but the extracted data should be scaled and matched to our spectra. So I think we are in the same page now. So this is how we can download, and you can see here in the peer website we can take it and we can match it and we can use for our site. So I'll come in a minute also. So once we get the data, so how to scale it and the spectral matching of the ground motion. So how we are going to match it as per UBC 97 and UBC 2000. Also I showed you the criteria, so let me discuss. So this is from any of this ground motion data we get the record. Now from the past record we get the data. So times 3, so we have ground motion scaling and a spectral matching. So we can use spectral matching or scaling. Generally in the range of 0.2 T and to 1.5 TN. This is how we are going to scale it. So a real earthquake, the advantage of ground motion scaling. A real earthquake, no change in frequency content. So when we scaling, I mean when it is up or down, we don't change any frequency content of the ground motion. Whatever ground motion we have here, we don't change any frequency content or anything. We simply make it up or down. The amplitude, we are playing with the amplitude. So that's what it says. Retain natural variances. Allow to focus responses on the period of interest. Relatively easy to perform. Disadvantage, requires a lot of time histories, greater variances. Example, if the structure model perform inadequately, you cannot be sure whether it is due to the poor design structure or due to some issues with ground motion of their variance, because we are artificially modify scaling it up or down. We will not be sure that whether the problem is with our data or the structure. This is then spectral matching. We are going to use the spectrum, this Sesamo match. I will show you in a minute. Sequentially add or subtract the wavelets to the time history until its spectrum match exactly with target spectra, all time period. So we have all time period here, then we have to match it to our design response spectrum. These are the researchers who did all this. So advantage, reduce variability in response. So any flaws in the structure can be clearly understood from the analysis and responses. So we will see each time step we will find the response. Disadvantage, can result in unrealistic earthquake ground motion, because uniform hazard UHS is a smooth unrealistic spectrum. Because our design response spectrum is modified, but the original one is smooth, not in the code based one. Some important ground motion aspects may be lost. Directively effect pulse, so it's important to check and compare the characteristics of unmatched and matched time history. Okay, this is some example. For example, you have mean matched ground motion, individual ground motions, and 5% target response spectrum. Once we have target response spectrum, this one is it's not visible, but our target response spectrum is directly in the red part. Then once we bring, as I showed you, we have extracted 11 ground motion, then this 11 ground motion will be matched with our target response spectrum. Then our target response spectrum from 0.5T to 1.5T, it should not be less than 1.4 times 5% of the design response spectrum. That is what UBC and IBC and other courses are saying. So if the extracted data we brought from here, when we match it, if it is less than the design response spectrum, then we will not use it. So as much as we can, we have to follow that. Then this is spectral matching in the time domain and frequency domain. ETABS also support that, but in ETABS, once we match it, we cannot extract it. We have to use it there. I will show you in a minute again. This is also defining time history, load cases, everything we will see it. So software demonstration of spectral matching. I will show you now how to match. We have ETABS 2019 and RSP match. I never use with this one, but Seismo match 2016, I think, yeah. But ETABS 2019 also I will show you. So let me demonstrate that. This is a time history analysis procedure, and okay, let me go Seismo match. First I will demonstrate it in Seismo match. These are our data. I will take one of the data and I will show you. Okay, this is Seismo match, and we have Seismo signal. We have two softwares, we can use both, but Seismo match, let me open it. Okay, this is version 2021 notification. Version 2022 release is available. Would you like to visit the website? Okay. Let me close this one now. Okay, so as you can see, this is Seismo match. This is a student version. I mean, my account is a student, so it has some restrictions, and the tolerance also 30%, so the result we are getting will not go down from 0.2. Let me check. Okay, it's go down 0. I'll show you in a minute, but it will not go down from 0.3. So once we have Seismo match register, you can send email to their website and they will give you student version. So for example, open single for this demonstration. You can open single or you can open multiple files. For example, we can open multiple files, or for example here, let me go, okay, because this is the student version, let me go to single. By default they have their own record also, Chichi, all this Kobe, Lome, Parita, this Northridge, everything is there. I mean, this is by default, it comes from the software. You can use this also if it is okay for you, but for us, we already downloaded from peer website. So let's go to time history analysis, linear time history analysis, peer website. Now from this site, for example, let me take for example this one. Let me take Imperial Valley. Then you should feel this is first line. Where is the first line for us? The first line is 1 2 3 4, but you can directly choose peer NJ format, no need to. So from here the first line start from 5, 1 2 3 4 5, because this is our first line. Last line, if you go down 1281, this is the last line. Time step, the time step is 0.01. Scaling factor is 1. Frequency, this initial value, this let's use default. So peer ground motion, this is the format. But other formats, for example, we have only time and acceleration, and in that time also we have to use time and acceleration value, and other formats also supported here. So once it's okay, then make it okay. So you see directly the frequency, the UG the ground acceleration file is directly came here. So this is input. In the time series also we have acceleration integrated, velocity integrated into displacement, so you can directly see. And the time period also around 62 seconds, so you should check that also, because as you see around 62 seconds the total recurred, more than 62, I think 63, something like that. So you have to check that also, you have to check that, because the total period, the total time should be checked. Response spectrum, this is a response spectrum. This is RSN 164. Mean now we don't have, because we have to play. So once we know this, and we see that the acceleration, the peak is 0.16, so this is what see. After that we have to define our target spectrum. So our target spectrum can be from code. There is different codes here. You can, for us we use Eurocode 8, then elastic spectrum, and for our case it is 0.1, type 1, I think B, ground type B, and importance factor is 1 or 2 for us. So just check for your response spectrum as per the code, and once you are ready you can do this. Then spectrum from loaded accelerogram, you can directly take from that, or load spectrum from file, you can have your file, you can bring. But for us, that is the damping is 5% and everything, then we can say okay. So this is our target response spectrum. As you can see, our target response spectrum is until 4 seconds only, because this is a student version. We cannot we cannot have the data after 4 seconds, because for 8 seconds, 9 seconds in the displacement, in the constant displacement region, this says more much, you have to buy the original one to find. So maximum period 0.01, scaling factor 1, maximum period 2, tolerance as you see 0.3. If I make it 0.2 for example, it works or not? Okay, it works also. I don't know how it works. Okay, we will see it. If it works, it is good. Okay, this is the first. If you need again, you can bring another also. You can bring also another. We bring this one. Then let's go and bring also 881 here. Everything okay. 0.05 11 points in the last line here. 2247. Okay. Again, this is the second earthquake, as you can see. Then you can see. So we have two now. Let me bring the third one also. (881). Okay, this is lenders. Yes, okay, the same thing. Okay, so we have 3 now. We can have 11 or 12. Then after we do this, we just make do matching. Now it will start matching. It will start matching now. Now it's matching. Average misfit for lenders, RSN 164. Average misfit is 8.6. For RSN 881, 3.4. Maximum misfit is 27. We will see the misfits, but it is good. RSN 3757 lenders misfit is 5, 21%. Okay, so this one is the matched one. This is the as per our target response spectrum. Then this is a matched one. Then we will check it from 0. As per the code, as I showed you, from 0.5T until 1.5T, the matched response spectrum should be more than 1.4, around 40% up, higher than the design response spectrum. It's not allowed to be down. So we will see that. Then after this, original, this is matched one, time series. This is original accelerogram. Then this is a response spectra. We will come. As you can see, this is a target spectrum, the red one, the target spectrum. Then RSN 164, RSN 375, you see. This is a match. So this one, for example, is down. Again, RSN 164 and RSN 881. This is a little bit deeper. RSN 881. Yeah, this one. This is, you see, it is very huge. So in this way we can see. I will come back here. So matched accelerogram, this is a matched accelerogram. You can see the difference, especially RSN 375 is huge. This is comparison. Original is in the blue color. The original is in the blue color, and the matched one is here. So you see the mismatch, the misfits, and table. If you want, you can take table. You can use R programming, and you can draw or compare or whatever. This is a response. This is the mean. If you want to mean, you can select all this. Calculate mean spectra, save, then calculate mean spectra. Now you see we have 3, then the mean is like this. You see, there is misfits, but as you can see from 0.5 second until 1.5 second, this one is at least it is a higher instead of down, so the mean is like this. So if your Sesamo Match is not a student version, you can bring all your data here, ground motion data here. Then once you are okay with the mean, you can save the mean spectrum with a mean response spectrum, and you can apply it in ETABS directly, because as per the code, we have seen that if we use 3, then we have to use the maximum. Yeah, so as per here, the maximum is this one. This means RSN 375. We have to use the maximum means this one. But if you use 7 and more than 7, we have to use the mean of the values. So you will save the mean spectrum, and we can directly use it for our design, time history design for non-linear or linear time history. We can use it. So in this way, we can use Sesamo Match for even also here ground motion parameter. You can see maximum acceleration 0.16, maximum acceleration 0.136. Okay, and maximum velocity, this one and this one. So this is ground motion, the matched one, and this one is the original one. You can go through and you can see the difference between the frequency contents, characteristics, intensities, and everything can be here. And you can, if you want, you can extract this data also. Right click, copy the entire table, and you can make any data you want. In this way, then this is the first method. But the second method is where ETABS itself has the criteria. I mean, ETABS has its own. So this is time history analysis, linear model. So in ETABS, what you can do, first, this is the response spectrum. Then you have to, this is our target response spectrum as per Ethiopian standard 815 target response spectrum. So modify, let me show you. As you can see, this is our response spectrum. So ground motion 0.1, soil factor 1.35, TB, TC, TD, all this was discussed in response spectrum, how we find these points. And but this is our target response spectrum. Once we know our target response spectrum, then we will go to time history analysis. In the time history, this is a matched ones. But what you have to do, if you want to bring, you go here from file, then you will extract all the file you want. This one, just to demonstrate, I took 11 here. For example, we have 11 datas. This is mean spectrum. The mean, how I take the mean, I will show you. So wait, let me go out. This is all the data I took. This is 4 datas, and I have 7 datas here. So just to demonstrate, let me open new ETABS. Let me open ETABS. Okay, let me close this one. For example, let me open ETABS just for demonstration. because we have two methods, SESMO match, and ETABS also has a capability to match the response spectrum directly, but we cannot take out the matched data from ETABS, but in SESMO match, as I showed you, you can directly extract. You can directly extract. Okay. Okay. Let's open, for example, new model. Just for demonstration purpose. Okay. For example, grid only. Okay, let's use as it is. Okay, now let's go define function response spectrum, add new function. For example, okay, let's use from SS and S1. As we have seen, we have SS and S1. Let's say this is okay, and the longer period 8 seconds B, and like this. Okay, so this, let's say this is target response spectrum, target response spectra. Let's say this is our response spectra. So okay, now we go here, function time history. From time history, what we are going to do, open from file. Now it will take us to from where we are going to bring our response spectra. It's a little bit slow. Add new function. Okay, function 1, let's say demonstration. Okay, browse. Let's say this ground motion. Let's say which one I open, the first one, 164. Okay, now as you can see I brought, but nothing happened here because header line to skip, this one 164, this is the file I brought, 1 2 3 4, so we have to skip 4.4 lines. As soon as I put 4, almost the data comes. So prefix, we don't have any prefix, some have prefix. Number of points per line, number of points 1 2 3 4 5, we have 5 points, and value at equal interval the value at equal interval, we have 0.01. This one is 0.01. Yeah, free format, everything. So once we did this, then when we say OK, then the file comes. Okay, the file comes. So this is a file we have now. Okay, this is a file we have now. So how to match it? We have to go here, match response spectrum. First let's make OK, then we go here, response spectrum, then we go here, match response spectrum, then add new function. For example, this one is matched response spectrum. So as you can see, we have a spectrum matching in frequency domain and the time domain. So the most important thing now, target response spectrum, as you can see, we have already the target. You see, this one is our target response spectrum. So the ground motion acceleration time is 3. This is acceleration time is 3, and the time, the response spectrum acceleration unit here, what unit we are using, you should know, because I am using with if it is inch or meter or G, we have to put. So for us, we are using meter. I remember I made meter, but for this one is G unit. This is G unit. So this is G unit, but for us we should check. It is G unit, but if there is any problem, we will see. So in time, in matching in frequency domain or in match in time domain, both are the same representation, as you know. So once it's okay, then match time is 3, then it will start matching. It will start matching. So as you can see, this is target, the matched response spectrum, and this one is a reference match acceleration time. The first one was here, as you can see, but the matched one is here because it's very high. So in this way, this one also used. If you want, you can bring another also. So it is already matched. So spectral matched acceleration, when it is matched already, it's go down. You see, the original was this one. It seems good because it's with our. So in this way, we can match all our. Then when you say OK, then the matched one comes, modify show. This is how we can see. So show frequency content or plot match time history, plot both, set parameters or plot time history analysis, everything is here. For example, set show the frequency. This is a Fourier series. This is how the frequency content looks like, and this is the matched one. This is closed matched. This is, we can do in this way. We can match it whether in the frequency domain or in the time domain. In the frequency domain or in the time domain, we can do like this. So we can match all of them like that. So there is nothing I can show you. This is the only thing we have. This is a plot for matched time history, matched yeah. So everything, set match parameters, show frequency content, user D. If you want, you can change it into user defined also. So in this way I matched it. So let me close this. No, in this way I matched it. So let me go to our file. So this is our time history analysis. So let me show you now all the material properties section, everything, these functions, response spectrum. So time history, the time history I use 11 datas. All we can see, for example, RSN 104 North Ridge, modify show. You see, this is the RSN North Ridge data. This is RSN 150 Chichi, modify show. This is Chichi earthquake, Imperial Valley. This is Chichi, again Imperial Valley. So 11 earthquakes we have. Then as I showed you now, all are matched. For example, this is a matched RSN 230 Mamos earthquake. You see, the original was here, but the matched one is almost okay. In the X, in the Y, both I matched it. In the X, in the Y, it is all matched. This is also lenders. As you can see, lenders also matched, because this was original, but when we match it almost as we need it. So this is how we matched it. This is how we matched it. And if you want, you can see view response spectrum. If you want to see the response spectrum for the mean or everything, because we have 11 ground motion, as you can see, for different damping, 0, 0.2%, 3%, 5, this undamped condition 7, 10%. These are all the X, Y. These are all the, this is the mean, this is the matched ones. So you can see pseudo spectral acceleration is paired. So plot spectra selected history, or if you want the mean, you can make it mean. Plot mean spectral for selected, you can select, and you can see the mean also. You can see the mean. This is the damping ratios. So it has a lot of applications, as you can see, for different damping ratio. It's obvious when the damping is low, the spectra is high, but the damping is increasing, so there is a decrease in our response spectra. By doing so, we can see the response spectrum. And once you have the response spectrum, you can make file. If you want to take out, file, this one, print data to file. We can take the data to file to use for our response, for our design. So if you do like this, then you can take the mean of all selected, because we select all our data. So you can make the match, only the match ones. For example, you can uncheck this. We can uncheck this, then because for our design we need the mean, then we can take the mean for our design. Okay, so by doing so, we can see our results. So let's go to this is, so as you can see, I matched almost all of, in the X and in the Y direction, in both direction I matched it. And now in the load case, again in the code, as we discussed, we should apply it in both directions, u11 and u21. So the most important thing is the load type is time history, and as you can see, linear model, we have non-linear model, fast non-linear time analysis, and we have linear direct integration and non-linear direct integration. So for this case we are using linear model, and we just use linear model. So for linear model we have to have model, and it is transient, not periodic, so we use that. Number of output time steps, each time step, this time step 6382 6382 0.01, everything should be as usual. Model, again model mass, we use constant damping for all model 5%. We have a lot of choices for damping, what kind of damping we have to use, everything. And for the model also, we have here model, modify, this is model, eigen, we choose eigen, mass source we have here, use p delta analysis settings, and we have 20 modes, and maximum number of mode, minimum number of mode is 1, and maximum we make it 1. So we have model analysis already. So all the earthquakes are here. So this is the load cases, all Imperial Valley, Lenders, Mamas, Lenders, Loma Perita, every and the mean also is here. So we will run our analysis. It's already run. Load case all is finished. As you can see, everything is finished, so no need to run, already run. But let me show you the outputs. So for our 44-story building, we can, for example, load, you can choose any, for example, Lenders or the mean spectra or whatever you can choose here. This is load case, the time maximum or whatever, or for example at 10 seconds, what was start time, for example. Okay, apply. I have the video because this one will take time, no problem. You see, this is the deformed shape in the tens means 1000. Then you can step like this. This is 101, this is 102, this is 103, 104, like this. And if you start animation, you can continue like that, the whole history, or you can start animation also. Okay, let me stop it. Option, animation sound. Okay, the animation sound is gone now. So we can see like that, as I showed you. For everything, for all the loads here, we can see like that. All the load cases, the mean, everything, we can see like that. We have the video, I will show you. And if you want to see the responses also, for example, for the moment, for example, Lenders, for example, Lenders earthquake, for example, in the 10th minute, what was the moment, because this is time history, each second, each time step, as you can see, each time step the moment envelope is changing as per time steps with our total earthquake. So what we have to do, for example, this is our moment. So once it is open, let me show you. We can go here, create video, multiple step analysis. So for example, just for demonstration, okay, sample, this is 44 story, output video, this is lenders earthquake. So let me open lenders and okay, save it. So once I save it, if you remember, it is 64 the total the input, around 64 seconds the earthquake. So from 0 start time, from 0 64 time increment 0.1 frame per second, this one frame size, this one. Though let me create because each time step the shear force, the story drifts, and everything is varying. That is the beauty of time history analysis. That's why it will capture the global and the local responses for each time period as per our matched time history analysis. So it will take time. Until it finish. Let me open some of the videos. I have videos. So this is sample building. For example, let's start from 44 story output. This is all the report. It's very huge report you can find. This is a video for Imperial Valley, for example. So let me open it. This is a moment until it captures, because it will take time to extract. The same thing, I use the same procedure to make videos. As you can see, for this ground motion, each second the shear force, the moment, I think the moment is varying. It's not constant, because I will show you in a moment the combined response spectrum. For each time step, this is the direction in the X and the Y direction. As you can see, X, Y, Z. So in this way we can see the response of the structure each minute. Again, the next video, this is a combined response. For the combined response, I will show you also in a minute. This is a record one. So for the North Ridge US earthquake, the ground acceleration, the matched one, we directly here, then we can follow and we can see the responses, the global responses and local responses according to the UG dot or the ground acceleration as per the ground acceleration file. But we are using it, the matched one, and the original one also used, but it is very huge. This is linear analysis, and we can use R factors. This is all the, this is a UGD now Imperial Valley US 164. So this is overturning, this is shear, this is drift, and this is the displacement will come. So this is the displacement, this is drift, this is shear, this is overturning. We can make it maximum, and once we start, as per this, the response, let me take it a little bit fast. As you can see, when the ground acceleration is varying, then the response of the structure, 44 story, the response of the structure is also changing. You see, especially around here, maybe it's very high. So this is minimum and maximum, and this is the time step 1, 1, 3, 6, 7. It will continue. This is a time step as per each division. So the responses, this response will be used to compare with the response spectrum analysis procedure. So for all the earthquakes, in this way we can see, and this is also the deformed shape of the structure as per when the earthquake was applied. 44-story building, as you can see, it's shaking. It's shaking the whole length of the earthquake. This is how the building is acting because of Lander's earthquake. This is also just section just to see the shear force, how it varies. Just to save time. This is also the shear force for the 64 second of earthquake, Lander's earthquake. This is how throughout the building the shear force is varying. Just to save time. This is for the shear wall. As you can see, the contour also varying. Lateral earthquake resistance systems, whatever you have, you can see like this. And yes, so this is for 44-story building. The same thing is true for 100-story also. If you go 100-story video, okay, this is deformed shape. Let's see the deformed shape first. This is a deformed shape. Imperial Valley 1979 earthquake. Hundred story. There is motion in the beginning, as you can see, it's moving. Now as you can see, when the earthquake around 39 seconds, still is moving. Yeah, it has movement, not that much. So this is Imperial Valley 1979. Lenders. Okay, let's see lenders. Let's start from bending moment. This is a bending moment, RSN 8810. Okay, so now it has movement. For me, I can check, I don't know for you. You see, different modes. I can see first mode, second mode. This is how the building is moving. This is lenders. This is just for the scale factor, because of scale factor. So this is a movement and the deformed shape as per lenders earthquake. It's shaking. Now start moving, as you can see. The same is true. This is how the building is maximum deformation, displacement, shear force, moment, or the four global responses will be used for comparison with RSA. This is for shear wall, F22 shear wall. Here it's not moving, but the next video I can show you. Yeah, this one. This is how varying. I make video until here. Yeah, this one when I zoom it. Okay, so this is how for all the earthquake, if you have time, we can extract all. You see, still it's extracting. It needs time for extracting, but for me I took a lot of time to extract this. Okay, so until it finished, let's go to our presentation to finalize what we have. Okay, so as per our discussion, we have done. In order to verify the result obtained from response spectrum analysis, dynamic linear time analysis was performed. So actual dynamic analysis can capture all local fluctuation and responses also. However, static analysis alpha and RSA are unable to capture local fluctuation and dynamic amplification results. That's why we are doing dynamic analysis. But dynamic time history can capture local fluctuation. As you can see, every second we can capture local fluctuation and response because it contains inertial term and the effect of damping. Hence it is expected more accurately to capture individual fluctuation of response from element to element as compared to alpha and RSA. So linear response history analysis procedure, as we discussed, direct integration method, modal superposition solution. We have this. Choosing the right ground motion is very difficult, as you can see. Not difficult, but it needs time, and from peer website we already extract and we use it as per Ethiopian standard 815 recommendation at the recording station. The selected ground motions have shear wave velocity 30 in the range of 360 and 800, and an STP value below 30 centimeter, greater than 50, CU 250, to make it consistent for designed model frame, because equivalent ground type and ground type B, we use this one, ground type B in Ethiopian seismic code respectively. Table 18 displays a selection of 11 unscaled ground motion from around the world. The selected recording station have horizontal acceleration between 0.089 until 0.75 g, and they are then matched to elastic response spectra ES15, as we see. Soil B PGA of 0.1 g, soil class B was used using seismomatch and ETAPS, as I showed you my demonstration. And according to the ES815 recommendation, the lowest and maximum matching period 0.T1 and 2 second to T1 respectively. T1 is a fundamental period of vibration of a considered model frame. So in this, as we have seen, it should be as per UBC also, as per IBC also, the same procedure. So these are lenders US 1979, lenders US 1992, Mamax 1980, lenders US 1992. The difference is recording stations, and lenders also Chichi, Norway, this Northridge, Chichi, all this earthquakes was extracted and used. Then for the dynamic analysis, the basic linear model approach of model analysis and response spectrum analysis modeling approach are identical. This one, the model is the same, so we used for 44 and 100 story building, we use the same building because this is linear. This is the material property, and this is the time periods and modal participation factor, which was we have get, and this is seismomatch ground motion. This is how we match it. We took all the 11 and we try to match it, and this is a target response spectrum. This is in the ETAPS response spectrum. Damping ratio, almost different damping ratio. This is for imperial body. This also I have showed you, so no need. Once you have matched, I matched all the ground accelerations to our target response spectrum. So this was, I will show you in a minute also. So just this is also for 100 story, we use 50. This is what we do. So the discussion, all these are the results, and it will be we will make it public when published. The final paper will be published, and all the discussion, the results, the findings will be available. and this is the next part will be non-linear dynamic modeling. So this will be the next will be the fourth part of the video, that will be for pushover analysis. So we will see what is pushover analysis, what kind of pushover analysis are there, and how to make our model. Until now we were doing with a linear model, then we have to see how to change it into non-linear. So for this purpose we are going to use plastic hinge modeling and fiber hinge modeling as per different guidelines and codes, and we will apply the first mode forces and uniform forces for nonlinear pushover analysis, and we will see, we will continue. Then after that, for verification, nonlinear time history response history analysis will be done, and all the results, outputs and everything will be discussed in the next video. So for this video our intention was, the objective was to demonstrate linear time history analysis. So this one is still continuing. It will take time, as I told you, it will take time. So everything I want to show you in this video was covered already, the results and everything, and this one is still extracting. So I showed you the videos, I have showed you the videos, and if you see the result also, you can directly project report, summary report. For example, from the summary report directly we can extract from the software. Still extracting. Okay. So this is a report, as you can see. This is summary report, dissertation project report. This was extracted here. Dr. Anna Evangelista and Professor Vivian was here. So everything is here. Everything what we consider for this report was generated like this. In this way we can have a full report of the design. I think just to see, for all the buildings we have the extracted original reports. So it's a little bit slower. Just I want to show you the page. Nothing, everything is completed already. Okay, this is how the report will be generated. As you can see, it's a huge report, around 152 pages. Only 100, okay, 152 pages. Okay, so this is the final I wanted to show you. Okay, let me cancel this one because it will take much time, as I told you. Okay, I cancelled it. So for display we can go here, story response plots, response plots, and directly we can, as you can see here, this is a final. I want to show you the load cases. We have all the loads here. For example, lenders earthquake, for the lenders earthquake, and the time, for example, maximum or minimum. We can make the maximum or the minimum, and or a specific time. This is in the x and in the y, because we have in the x and in the y direction. This is the displacement. You can see 574 in millimeters, around 57 millimeter was a story displacement. The same thing is story shear, story moment, overturning moment, story stiffness. Everything can be seen here. For example, center of mass displacement, again diaphragm, drift. We have drift also. As you can see, this is the maximum drift ratio, around 0.5% was the drift, and maximum story displacement. This is 44 story building. This is a story displacement, and story shear. The shear also can be extracted. The shear also can be extracted, and for each, this is a kilonewton. This is the kilonewton, and the moment also, overturning moment, like this. And if you want also for particular beam or for particular, this also the moment. In this way we can find out the outputs. Again, load sets, or here earthquake in the x, in the y. You can change this also. Load sets, you can put here story range, diaphragms, all are here, and you can save the plots, or you can again summary report, detail report. You can find, you can directly take from here. This is what I wanted to show you. So this is a result, and this is our building. The same thing is for 100 story also. So in this way we can do this. This will be the end of this video. I deeply would like to thank you, Dr. Anna Evangelista and Professor Vivian, and we shall meet in the next video. Thank you so much.